Okay. Can you hear me? Can you see my screen?
Yes, all is good.
Okay. Sounds great. Thank you so much. I'm very happy to be here and tell you something more about my research. And yeah, let me just get rid of this bar. Okay, here we go. So first of all, let me tell you something more about my research lab. So the name of my research lab is SMMS, Smart Multifunctional Material Systems Lab. And we are in Iowa City, in the US, in the Midwest. And I currently have 6 PhD students and a few undergrad and visiting scholar in my lab. And what we do is summarized here on the right. We work on bio-inspired materials in general, smart materials, multifunctional nanocomposites, and we also do in general multi-scale characterization of engineering materials. We work with materials that can change colors, as you can see in this video, but also shape. And I will tell you more about that in a little bit. And we also work on some electromechanical piezoelectric materials, and we also work on rehabilitation robotics. So today I will be focusing mainly on bio-inspired materials and artificial muscles. And this is the outline of my talk. I will give you a brief introduction on artificial muscles, and then I will describe 2 different types of artificial muscle we make in our lab, and we call these TCAMs, twisted and coil artificial muscles, and TSAMs, twisted spiral artificial muscles. So let's start with an introduction on artificial muscle. The first question is, of course, what is an artificial muscle? So when people hear that I work with artificial muscles, they usually think I work with biological tissues, but actually it's not like that. For us, artificial muscles are 100% synthetic engineering materials. And the main definition of artificial muscles, it's here. Basically, an artificial muscle, it's a material or a device that can reversibly contract, expand, or rotate within one component due to an external stimulus. So one component here, it's the key word, because we just have everything in a single component that can be a single material or multi-material. Then the second question is, what do we want to emulate with artificial muscles compared to skeletal muscle? Now, you may be familiar with the mechanism of contraction of skeletal muscles. So we have a few fibers inside our skeletal muscles, and then we have actuation related to a sliding mechanism between actin and myosin. We don't want to emulate this actuation mechanism because it will be very hard from an engineering point of view to achieve a strong actuation with a sliding mechanism. What we want to emulate from skeletal muscles are mainly the functions, so the low weight, flexibility, and efficiency, scalability, and force. The last question is, what is different compared to conventional motors and actuators? I really like this plot because it gives you an idea on what is the main difference between conventional actuators and artificial muscles. Here you can see that we are plotting power to weight ratio versus weight. You can see that there is a clear trade-off of current actuators, and you can see that their property lie along this line. So you can either have an actuator like a DC motor, for example, which is very lightweight, but at the same time, it doesn't provide a huge power in output. Or on the other side, we can have turbine engines, which can provide a big power to weight ratio, but at the same time, they're very heavy. But if you take a look at this plot, you see that in the yellow area, we have natural muscles, which are our skeletal muscles. You see that they are on this left side. So they can provide at the same time a high power, and they have a very small weight. And this is very convenient for us for any kind of applications. And that's what we are trying to do with artificial muscles, which are in this purple area here. You see that we are in the top left corner here. So with artificial muscles, the idea is to provide a large power to weight ratio, but to have a very lightweight device. And here I just try to summarize a few types of artificial muscles that are pretty well known, and we have, for example, shape memory alloys that they can remember a specific shape according to a temperature profile, but they are very expensive, and they're very hard to control because they have a pretty big hysteresis. Then we have electroactive polymers. They can actuate a lot. They can contract and provide a big deformation, but the main disadvantage is that you need a super high voltage in the range of kilovolts to actuate them. And the other option might be pneumatic artificial muscle. It's just a bladder that you can inflate, and then this can contract. But for that, you need to carry a heavy and big compressor. So if we take a look at the plot stress strain, so stress, it's the weight that they can lift, and strain, it's more how much they can contract. Also, in this case, there is a trade-off. So either you have something like dielectric elastomers or electroactive polymers that can provide a big contraction, but not a big output force, or on the other side, you have other materials like, for example, shape memory alloys. So what we try to do with our artificial muscle is to overcome this trade-off one more time. So what is a twisted and coiled artificial muscle that we call TCAMs? It's a very simple, it's super easy to manufacture. So you start with a straight fiber, you apply a load at the end, and then you highly twist this fiber until you induce spontaneous coiling. So your initial configuration is a simple coil. Then when you provide an input, which can be simple heating, Joule heating, or even other different chemical input, you can have a contraction. Now, we have a few types of artificial muscles that we can call TCAMs. We have carbon nanotubes based TCAMs, polymer based TCAMs, and our new type of TCAMs, it's based on carbon fibers TCAMs. So this is how we make it. We basically start with a toe of carbon fibers. We dip these inside an uncured silicon rubber, which is a PDMS diluted with some hexane so that it's less viscous. Then we twist everything, and then after this is twisted, we just place it on a stage to cure the PDMS. Here on the right, you can see that the final product at the end of this curing is just a yarn of carbon fibers and PDMS, which are twisted. Now, once you have the curing of the PDMS, you keep twisting everything while you have a weight at the end, and you induce spontaneous coiling. So that's it. This is our artificial muscle. Now, here it comes the magic. When we give an electrical input here, like in the video on the left, you can see that these artificial can contract. And the same thing can happen if instead of using just Joule heating or simple heating, we use as well, which is the matrix, can absorb this solvent and can swell, and then we can get contraction as well. Now, in terms of performance, the good result is that this tiny artificial muscle, as you can see here, there is a ruler, and it's only just a few centimeters long, and the thickness it's less than 1 millimeters. It weighs only 0.061 grams. And we were able to lift up to 770 grams with this artificial muscle. So this means that these TCAMs can lift up to 12,600 times their own weight. And in this video, we show how with this tiny muscle, we can lift half a gallon of water of a few centimeters. This is an inch scale on the left, just with a very, very small input voltage in the range of 0.2 volt per centimeter. So if we go back to this stress versus strain plot, our artificial muscles are here. So we are basically going in the other direction. So we are starting to fill this top right corner here. And with these artificial muscles, we can provide at the same time a big actuation, and also they are very strong. So we can overcome this trade-off between stress and strain of current actuators. So the big result is that they are strong. They can lift up to 12,600 times their own weight. The specific work that we achieve is 18 times higher than that of skeletal muscles. And the other two good news is that they are very cheap. They can just be produced with 0.1 cent in terms of input voltage, we only need a small battery to actuate them, because we don't need kilovolts. We just need 0.2 volts per centimeter. So it depends how long is this artificial muscle. Now, we developed a few theoretical models to explain why these artificial muscle actuate when we provide an electrical input. Now, I will go quick on this because I don't want to bother you too much with a lot of equations. But the main idea is that we started with an energetic approach. We model the total energy of this system, and then after equilibrium condition, we reach this important equation here in this box, where we have beta, which is the coil angle of our final coil, and then we have B and C, which are the bending and the torsional stiffness related to our Young modulus, shear modulus, and the radius of the yarn, and then we have T, which is the external tensile load, and R, it's related to our number of turns. Now, why we have contraction? We have contraction because in order to have a TCAMS, you need to have a very important ingredient. You need to have what is an anisotropic volume expansion. So basically, you need to have a material that, when heated, can expand along the radius, but it does not elongate. And this happens to carbon fibers. Now, you can just theoretically just use carbon fibers to make a TCAM. The problem is that the coefficient of thermal expansion is small, so you just get a small contraction. But we increase this expansion with PDMS. So the ingredients are two in this case. You have a big volume expansion, and in this case, this is given by PDMS, and then you have anisotropic volume expansion, in this case, given by carbon fibers. In terms of equations, what you have is that once you have this anisotropic volume expansion, you have an increase of the radius of your fiber while your length is constant. Then you are changing the bending and the torsional stiffness, and if you go back in the previous equation, you are changing this coil angle. This beta is increasing, and then our equilibrium condition, it's this one on the right, where it's just a stiffer coil with a bigger radius of the fiber, and then a new equilibrium position, and then we have this contraction. And then we explain this in our paper with a very simple static model. Now, once we have done the static model, we also developed a dynamic model to describe how this contraction changes with time. And this is a simple second-order system with a spring dashpot mass, and this is a physics-based model where we model the stiffness of the material related to our mechanical and thermal and electrical properties of our materials, and then we can describe this actuation as a change in the stiffness of our system. And this is what we did with this dynamic model. And here you can see the validation of this model for thermal actuation. Here we just heated with a heat gun our artificial muscle, and then on the right here, you can see that the full line is our model, and this colored line are three different results for three different samples. You can see we have a nice agreement between model and experiment. So basically, with the thermal actuation in our model, we model mainly 4 steps. We first model the radius increase due to temperature increase, step number 1. Then step number 2, we model how this temperature increase causes a change in bending and torsional stiffness. And then step number 3, how this stiffness change causes a change in our coil angle. And then finally, step number 4, our contraction and our displacement. We did the same thing with an electro-thermal actuation. In this case, we have visual heating. So we just have an additional step, which is step number 1, where we model the input voltage and the relationship between input voltage and the temperature that we reach. So with our model, we are able to tell you that if you're looking for specific contraction, you need to use a specific input voltage. And this is a completely physics-based model because everything is related to the properties of our materials. Finally, we also developed a robust and adaptive control, because now we are making some robotic devices with our artificial muscle, so we need to control in detail how they can be actuated. And this is a very robust controller that is able to guarantee safety at low cost. It's so robust that we can use very cheap hardware with a very bad acquisition rate. And at the same time, we can minimize the sensors on board, because we don't need to measure, for example, the temperature of our artificial muscles because we use some observers in our controllers. So we just need to measure the displacement. This is how we implemented the controller with Simulink and ROS, and then this is how we are able to provide a contraction target, which is the desired displacement is the blue line here on the left, and the real displacement is the desired displacement is the red, and the real displacement is the blue line. So they match perfectly. And a simple PID controller, for example. Then we also proved that these artificial muscles can behave like skeletal muscles. So if you take a look at the main biomechanical properties of skeletal muscles, you will see that they have at the same time an active and a passive force. So they can contract, but at the same time you can stretch them passively. So if you take a look at this plot D here, these blue lines, this is the active passive plot of a skeletal muscle. So we have an active force, and then we have a passive force, and the force that you have in output is the combination of these two. Now, in robotic devices or rehabilitation devices, usually people need always two ingredients. They need an ingredient for the active force, like a DC motor, and an ingredient for the passive force, like a spring. With our artificial muscle, we just need one ingredient, because we can provide at the same time active force. When we provide an input voltage, this coil can contract, and also passive force, because this is also a stretchable coil. So with this plot here, we show these red lines that we can plot C. We can have active and passive force at the same time, but in terms of numbers, we have bigger values compared to skeletal muscle, because here we can reach 60 megapascals in terms of stress, while here on the right we can reach only 0.1 megapascal with skeletal muscle. This plot in blue refers to the brachii muscle, which is this one here. And so the great advantage is that with our artificial muscle, we can get rid of very heavy power sources, very heavy actuators, and then we can provide a lot of degrees of freedom, because we can use a lot of these muscles to reproduce the arrangement of skeletal muscle in our limbs. So you can see here on the left a current device for upper limb rehabilitation, which is pretty bulky, and it's mainly made from rigid links and electric motors. But with our artificial muscle, we can make very wearable sleeves with a large number of these tiny and powerful artificial muscles. So we can overcome the trade-off between portability and multifunctionality, so the number of degrees of freedom that we can provide. Currently, we are working on prototypes for both upper limbs and lower limbs. This is an example of an exoskeleton that we developed using our artificial muscles for upper limbs. In this case, it's for wrist rehabilitation. And these are our artificial muscles just covered with an elastomer tube, just to provide electrical and thermal insulation. And we tested this on a 3D printed limb. We proved that we can achieve the same range of motion of healthy individuals for extension, flexion, radial, and ulnar deviation. Then we also proved that we can actuate this exoskeleton with EMGs, electromyography sensors, that can detect the input from our skeletal muscle, so that we can control with our intent the device as well. And this was the first part of a twisted and coiled artificial muscle. Then we also developed some a different type of artificial muscles that we call T-SEMs. The mechanism is still the same, but in this case, instead of having a helical shape, we have a spiral shape. So while in the first case, once you reach coil-coil contact, you are done with your actuation. With the second case, if you have a spiral shape, you can basically go up and down and have a very big actuation without having the problem of coil-coil contact. So this is how we make this artificial muscle. We highly twist a polymer fiber while we wrap around a copper wire, and then we shape this into a spiral. Then after an annealing process, we have this nice spiral. When we have to prove some input voltage, we have this actuation. So with only 0.2 volt per centimeters, we can have a stroke, so a contraction, in this case an elongation, of 2000%, which is a pretty big result. And my students also developed from scratch a manufacturing machine to make a lot of these artificial muscles at the same time, and we reduced the manufacturing time by 75%. Now, in terms of model, also in this case, we modeled the actuation, and we got an equation that can describe basically the change of the radius of this fiber related to our output displacement. And this is some model validation for both free vertical displacement and the displacement with the load on the top, and we have pretty nice agreement. We also developed a dynamic model in this case, and we model all the steps that I mentioned before. So you're hitting a radius increase, then this radius increase causes an internal untwisting and then uncoiling, and then this vertical displacement. So I won't go into the details because of lack of time right now. So, but we developed all the main steps of this physics-based model to describe how you can relate the input voltage to the output displacement. And again, this is a completely physics-based model where you can basically make your recipe of your own artificial mass in terms of materials to achieve the displacement you're looking for. And this is a test where that we did, where we provided an input voltage here on this plot. This is a step, and then we measured the temperature over the thermal camera and the displacement here with a normal, just with a phone connected to MATLAB. And with these experiments, we validated our theoretical model. As you can see here, the red full line here is for temperature, and the blue line on the right is for height, which is the vertical displacement. And we have a pretty nice agreement for different samples with different geometries. We made samples with copper wire for electrical actuation and with silver paint as well. And also in this case, even if results are a little bit more noisy, we have a good agreement. And then finally, what is the application of this second type of artificial muscles? In this case, the inspiration comes from an octopus, from cephalopods. I'm sure you are aware that the octopus is able to perform camouflage, as you can see in this nice video. But camouflage is not only color change, it's also texture change. So if you take a look at the skin of cephalopods, you see that they have some dermal muscles, which are called papillae, that can go up and down, and then that's how they change the texture of their skin, and then the skin can be very smooth and flat, or it can be very rough. And that's what we are doing with these artificial muscles. So here on the left, you have the video of the skin of the cephalopods, and on the right, you have our artificial muscle that can exactly behave like a papillae muscle of cephalopods. So when you embed a lot of these artificial muscle inside an elastomer matrix, we can make what we call a self-morphing skin, which is very thin, and you can actuate the actuation of this muscle to achieve a specific texture. And then we deposit with spin coating a top layer so that we make everything also waterproof. In terms of application, you can use this skin to change the roughness of underwater surfaces. You can improve the drag, the hydrodynamic drag. You can induce the turbulence, for example, and you can also use this as a 3D display or even a braille display for people with visual impairment, or for haptic feedback devices in general. This is a video where we prove that with a simple microcontroller, we control the actuation of these artificial muscles, and then we match a texture that we have here, this bottom right corner, which is a target texture. So we can do this with and without a top layer as well. Then the last step that we did in terms of manufacturing was to avoid floating wires. So we wanted something that was completely stretchable and waterproof. So we use some 3D printing to 3D print some liquid metal electrodes to actuate these artificial muscles. We optimize this process. As you can see here, we can 3D print in a completely transparent elastomer these liquid metals with different shapes, and we also optimize with some simulation and modeling this 3D printed mechanism in order to make sure that we had a very continuous line and not some dots. And these electrodes are also super stable because our resistance increases just a few ohms when we stretch it by 350% or when we twist it with an angle of 700 degrees, which is quite a lot. And these are our prototypes. This is a smart glove with all these 3D printed stretchable electrodes, and it's a very thin 2 millimeters skin that can produce different textures. And then we also made, this is just a video to show the actuation of these facial muscles while we wear it. And this is also a prototype of a soft octopus that it's a soft robot that is completely waterproof. Here we have 40 artificial muscles embedded in this silicone octopus, and then everything is covered. And underwater, when we actuate this muscle, we can change the roughness of the skin of the octopus, and then we can also improve the hydrodynamic drag of this soft robot. And this is the nice cover of our latest publication in Advanced Functional Materials. In terms of application, with this skin, we can do a lot of things. Now, this project is currently funded by the Navy, here by the Office of Naval Research. And the idea is to use this skin also to detach some biofilms that can deposit on the hulls of ships. And this is a huge problem for the Navy, because when you have a deposition of these biofilms, you have a lot of fuel consumption and a lot of maintenance costs, because they have to stop the ships and then get rid of these biofilms. The idea is that with these artificial muscle that go up and down, you can release biofilms. And this is what we proved. Here we grew some biofilms with a specific process, and then this is just a device with one artificial muscle, and this is how the biofilm looks like under a microscope with some fluorescent dye. Now, in this next slide, these on the left are some pictures of our biofilm before the actuation of the artificial muscles, and this is our device. But after we actuate the artificial muscle only 10 times up and down, you can see on the right that we were able to get rid of our biofilms with more than 99%, or I mean almost 95%. Almost all the biofilm was released, as you can see, because you don't have much green left on these right figures. We proved that with different biofilms, with Cobbestia marina, E. coli, and even with some algae. As you can see here, a difference from the left and the right. And now we are doing also some experiments in the Iowa River, which is in front of our lab, to prove that we can detach biofilms also in streaming water. And then, as another application with some underwater tests, we proved that we are able to induce turbulent stripping, and we can induce a turbulent flow. And this is a very convenient phenomenon, because we can avoid the flow separation. Yeah, sure. I'm wrapping up. Thank you so much.
We're out of time. Please hurry up in going to the conclusion.
Yeah, sure, I'm done. Then we use turbulent stripping, and finally, in this final idea, we are using also artificial muscle to make some soft tentacles, which are very soft and lightweight and can be used for underwater robots. So that's it. Sorry if I took too much time, and I just want to thank all my students and all my funding agencies. So thank you so much.